Buenas tardes a todos y todas. Les damos la bienvenida al 7º encuentro del ciclo de charlas del Departamento de Física. Soy Julián Juan, soy licenciado en Física e integrante de la Comisión de Extensión y Difusión del Departamento de Física. Unos avisos. En primer lugar, pedimos que los y las interesadas en los certificados de asistencia comenten su presencia en la caja de comentarios mencionando claramente nombre y apellido. En segundo lugar, repetimos la novedad que contamos la vez pasada. Hemos decidido entregar certificados de asistencia a cada charla individual, además de los certificados de asistencia al ciclo de charlas a las personas que asistan al 60% o más de las charlas. El formulario se cerró el viernes 30 de octubre, por lo que no tenemos los mails disponibles de las personas que solamente asistieron a la charla del 6 del 11. Por lo tanto, hemos habilitado nuevamente el formulario de asistencia para que lo completen las personas que todavía no lo hicieron. Y ahí hemos adjuntado el link en la caja de comentarios. En cuanto a los comentarios y preguntas sobre la charla, pedimos que las agreguen en la caja de comentarios y serán respondidas luego de finalizada la charla. Yo me encargaré de traducir las preguntas y las respuestas. Terminados los avisos, tengo el agrado de presentar al teacher David Featonby. David Featonby es un maestro de física retirado, él es de Newcastle, Reino Unido. Él ha trabajado en el Institute of Physics y más recientemente ha estado involucrado en Science on Stage Europe como miembro del Executive Board. David es columnista de la revista Physics Education. Su columna se llama What Happens Next. En esta ocasión nos va a presentar la charla A Career in Teaching, What Happens Next. Terminada la presentación, le cedo la palabra al teacher David Featonby. David, I have finished your presentation and now you may start whenever you like.
Right. Well, hello everybody from over the sea, a long way away. It's very dark here and it's night time, but you still have the evening ahead of you. So I hope you will enjoy this session with me from England. If we click on the next slide, are you seeing the slide? Yeah, and then the next one. Go to the next slide. So I'm sort of thinking about a little bit about how I got to where I am, and then we'll look at what happens next, which is more the sort of science experiment side of things. But if we have the next slide, I've summarized, this is my life in science, really. You can see, you can work out how old I am because you can see when I was born. I went to an ordinary state grammar school, as many of us did. And then in '64, did my physics degree at Manchester University. I wondered what I would do at the end of that, and in the end decided that I wanted to teach and share my physics with some younger folk. And so what happens in England is you take your degree, your bachelor degree, and then if you want to teach, you take an extra year's course specializing in teaching and in your subjects. And I moved to Newcastle University then. And then I was very fortunate actually I got it wrong, in '68 I started teaching a physics at a school, big comprehensive school in Newcastle. It was a grammar school then, but it then became a comprehensive school with all abilities. And I started my teaching life with my fiancée, that we got married in the first year of our teaching. She taught maths and I taught physics. And we had a lovely time. The children at the school really enjoyed us getting married. I can remember they tied all sorts of things to the back of my car when they thought we were about to get married in the holidays, and that was fun. I don't think they'd be allowed to do that these days. all health and safety. So after a few years at the same school, I became head of physics in charge of the physics department. So 7 of us. And then I became head of science. That was looking after about 20 different staff. And then I had a bit of a swap and changed to be looking after the 17 and 18-year-olds in the school just before they went off to university. That was a really great job because I was sort of independent. I could do lots of things that I wanted to. And that was part of the senior management of the school. And then in the final years, I was promoted to be an assistant head. I remember we were all involved with setting targets and averaging things and so on. And the head came to me and said, David, you're the only one who can understand this maths and so on. So will you be an assistant head? So that was another change. Fortunately, all the way through, because physics is a shortage subject, still is in the United Kingdom, I still had some very good classes to teach. And I insisted all the way through that I had some very good classes and some very low ability classes, so that I wasn't just teaching the best, I was teaching the whole range, which was interesting. In 2003, they decided to reorganize the school, and in fact, I was offered what we call in England early retirement. It just meant that my pension would start early. So it was reduced pension, but it started early. And at the same time, the Institute of Physics were looking for people to support teachers of physics. So I worked for them half a day a week. It was like pocket money. It wasn't like a wage. But that introduced me to doing workshops and things for teachers. And I said at the end, after about 4 or 5 years, well, I've been out of the classroom for too long. Now I want to stop this. So I stopped and lost this extra money. But by then I was involved with this group called Science on Stage. And that became my hobby rather than a job. And this is what I do now. And so I have some lovely friends all over the world now. And in fact, what I do until COVID came along was about every month I went somewhere and took a workshop. We go to the next one. So, that's the next slide is sort of my life generally. You're not perhaps interested in that. I have 2 children. They're 47 now, and they've got twins. That was 1973. That was another lovely event in the school because my wife was still teaching. She left before she had the babies, but the whole school was knowing that we were expecting twins and so on. So anyway, we'll skip all the sort of general details of my life. We'll get on to some of the more interesting things. So after retirement, we go to the next slide. I was asked, come and give a talk. They think, old man, you've got experience, come and give a talk on nuclear physics or something like that. And I felt that really that wasn't what the children really wanted as entertainment, to be bored for an hour with some old man telling a talk. And I thought, is there a better way to go and share some of my enthusiasm? And I came up with this idea of what happens next. Because the other thing that always happens in England at the end of term is the children always say, oh, do we have to work on the last day? Can we have a quiz? And so I thought, let's have a quiz that is about the science if we move on. Because there's another bit of an issue in UK is how to really engage and motivate students and children in science. There seems to be a lot of enthusiasm in the primary school up to 11, 12 years old. And then I don't know what happens, but it's 12, 13, a lot of the children get a bit bored with science. There's another group who say, oh, it's hard, it's too hard, we can't do it. And then you have classes where there's only a few who really are involved. But how you can involve the whole class? That was a problem, to get people talking and so on. And we came up with this idea of what happens next. We move on. I went for lunch at Dundee University in Scotland with a professor of engineering. And he'd been researching why students choose engineering for years. And he'd come to the conclusion that he didn't really know, after all this research, that different children choose science and engineering for different reasons. The next slide. It's easier. Next slide. It's easier to say what puts children off science. It's the fact that they lose interest. They feel it's too hard and they can't get on. So the solution, I think, one big solution is enthusiastic teachers. We move on. I think I've got a slide. Top of the list to get children involved is enthusiastic teachers. And sadly, some teachers aren't very enthusiastic about their subject. And it shows. When I was in charge of a department, people would say, "Oh, we don't want Mr. So-and-so because, he's so boring. And can we have so-and-so?" And so on. So next slide. We'll quickly move through these to get children involved by having short demonstrations and experiments which lead to discussion, and try and do it in a non-threatening atmosphere. Now what happens next are a little bit one-offs. They're not maybe the whole lesson, but it is one way forward. Next slide. Next. So what happens next? It's interactive. It involves everybody. It develops thinking skills. It involves group activity, helpful insights into basic physics, and explores misconceptions. Because another problem that we have in England is often the first bits of science are taught by non-specialists, and they do get a few things wrong. So move on. Next. So can we bring the spirit of inquiry and excitement and interest into your lessons? Are the children with me? Quickly move on. Another one. We can use this technique as a starter for lessons, assessment, a quiz at the end, or something else. There's all sorts of things, but they are fun. Next. So this workshop that I'm going to show you now, I've taken all over Europe. It's really embarrassing that I've been privileged to be to all these different countries and learned a little bit from everybody. Next. And there's research that says that, you can look this up later, you can have the PowerPoint, different bits of research that talking things through is a great way to learn. How many of you teachers think, well, you really understood the first time you had to teach something? I was very good at physics at school, and yet I learned a huge amount in the first few years of teaching by having to share with others. Next. These ideas, primary and secondary, are quite different. I think the primary schools, the children, really you want to teach them good observation and the ability to discuss, suggest theories and ideas and so on. But it really is observation and discussion, hopefully in a scientific way, to move them from perhaps the fantasy that they have. Children aged 7, 8, 9 will believe anything because they see it on the television. They see cartoons with all sorts of things happening and they think, oh, well, that's just how things are. Secondary students want to be homing in on their own scientific knowledge, testing theories, and of course, discussing and debating, rather than just sitting, absorbing fact after fact after fact. Next. How I do this with secondary students, I will sit them around like that in a class, in groups, so that each table would discuss. Next, with smaller children, they're sort of quite like sitting in a group, and the whole class can sit in quite a small space to discuss next. But of course, nowadays, I should say, really, where these can actually be used as when you're doing online learning, although you don't get the discussion, but that's how things seem to be going for the next few months at any rate. But we're keeping students engaged with short answers and so on, and focusing on actual things rather than abstractions and so on. We'll move on, going through this very quickly, and move on to the next one. Move on again. This was interesting. Somebody's done this research that if on the right-hand side, the bluish diagram is a brain, how it works when it's just receiving facts. Whereas if a brain is really engaged in a story, look at the activity. And I sort of look back on my own teaching and wonder how many children sat in my class with that blue brain rather than the brain that's really engaged. So the idea of us teaching is to really engage with the students. You know, I think of teaching a lesson and having to pause and say, "Are you with me?" Do you know that expression? "Are you with me? Are you with me on this?" And, you know, the kids are looking out of the window, they've lost it. So that's the next slide where we can interact with the brains together. And so go to the next slide. So really we're wanting to take our children from this bored brain into the active brain. Right, I think we're nearly there. So move to the next one. So what happens next is a set of questions where we try to engage with the children in different ways. So we've taught a subject, and I'm going to give you 4 or 5 examples of the different types of question, and then we'll have a set of different examples where you can sort of work them out for yourself. So here we have the first one. Next slide. We're trying to reinforce something. So we've got a spoon, got one here, can do this for you. A spoon, and I'm going to say, get in the right picture so I can see. If I balance it on my finger, like that, and then I cut it in two, where the join is, I've got a bigger one here, which I use. This is a brewing spoon, so I can balance it, and then I cut it in 2 halves, like that, and ask the question, which is the heaviest half? So is the head, this part, the heaviest, or is this part the heaviest? Click onto the next slide. So I would give them perhaps these 3. You can go enlarge the slide. Both pieces weigh the same. Is the handle heaviest, or is the head heaviest? Because it's balanced. Now, I've done this with loads of people, and I can guarantee that a good proportion will give A as the answer. Both pieces weigh the same. But of course, even teachers will get this wrong. Of course, because it's balanced, the distance to the center of the head to the center of the handle is different. So click on. So we have the heavy head, which is a short distance from the pivot, and the lighter handle, which is a long distance. So it's just an application of the principle of moments. which you have, which is, they might have done a seesaw experiment. Next slide. So they've done this with the big person, the little person, so it's an application of that. But it's a nice little thing to get people talking. So you would let them talk about it. It's important for them to, if you're doing it in a class, to get people talking and thinking. Another nice one that I often start with, if you go to the next slide. Oh no, I'm one ahead of myself. So you could take something that is much more unusual, something that they may not know about, and ask them a question. These are quite good sometimes because sometimes the less able children get them right and the very clever children get them wrong, and that does the class a lot of good. So I wonder if you know this one. Move next slide. Next slide. Oh no, it is the one that I was thinking. This is an easy one. This is an easy one. Sorry about that. We've got two beakers, and here I've got them here, and they're both basically full. They're 80% full. Okay? And the question that I ask, and I often start a class with this, is if I try and pour this one into the other, perhaps I'll hold it in a dish like that, and I try and pour this one into this. How much will spill? They're 80% of the height, 4/5 full. Will it fill, I say, or will it spill? I can change it slightly, the question, to how much will spill. And for a bit of fun, if somebody says, oh, it'll fill, I say, all right, I'll do it over your head. And will it fill or will it spill? What do you think? Will you get all of this into this one? Right, well, let's try. And it all goes in. Amazing. And just put it down. And of course, the discussion can center around it's wider at the top, or you can discuss a third pi or squared h. You can work it out. I must admit, the first time I did this, I had this idea, and I worked out that it was, I think it was 0.82 of the height. So I carefully measured, you might even see a mark on my beaker, 82 of the height up, and carefully poured the water into that depth, and then poured it into the other cup, the other way. But of course, the best way to fill these is to have one full and then fill the other with it, so you get it right. Right, let's move on to the next couple of slides as we go through. The application of that, of course, is if you have some medicine to take, make sure you fill the spoon right up to the top, because if you see on the left, those two spoons look fairly full, but in fact they're half empty because you can pour one into another because of the wider top. So there are applications of these. Next one. Next slide. Yes, this is the less known area of physics. Now, you've got to be careful that you don't put children off by asking too hard questions. That's why doing the water and things like that at the beginning are fairly easy ones for everybody to get right. So this one, we click on, I have a very strong magnet, and two, I've got some glass, little glass rod, and some aluminium. The aluminium is here, and then I get a very strong magnet. And what will happen if you go to the slide back again? Go to the slide big. Go to the slide, next slide, and enlarge it. Swap me for the slide. So you can see there, that, I don't know if you knew this, I didn't know this until a few years ago, aluminium is paramagnetic. Apart from the ferromagnetics, which are the strong magnets, aluminium is paramagnetic. So when you hold a very strong magnet beside it, it is weakly attracted. And that means that the aluminium, the end goes towards the magnet like that. Whereas next slide, glass is diamagnetic. And so that is repelled by a magnet. And the way that it can be repelled is to go horizontal to the magnet at right angles to the magnetic field. Doubt if any of the children would get that, but it's just something that's in there. You can introduce very, very strange things just out of the blue. Next slide. Or you can try something where the outcome isn't quite as expected. Now, I love this one, and I remember the first time I came across it, my son was at Oxford University studying his PhD, and he got this wrong. So if you move on to the next slide, you've got two balloons. I'll just get myself ready here. I can do this. Two balloons, a big one, exactly this came from the same packet. If we were live and I was with you, I'd give you all a balloon to take home. So I blow one up fairly big and exactly the same packet, blow the second one up. This is a connector for a hose pipe, but you can use just a piece of pipe and some clips. Blow the little one up as well, fix it on. And what happens when I open the tube? Will the little one blow the big one up, or will the big one blow the little one up? What will happen? Or will they just stay where they are? And most people say that the big one will blow the little one up, but in fact, it's the little one that blows the big one up. You saw that? You saw that happening before your eyes. Why does the little one blow the big one up? Well, when is it hardest to blow the balloon up? When do you say, Mom, Dad, Mummy, Daddy, Granddad, will you start the balloon? The balloon is hardest to blow at the beginning, and that's when it's got much more pressure or force. That will do for the little ones. The older ones, it's a very, go on, can we click on? We'll just go back to the slides. And there's the sort of alternatives that I'd give people, and then click on again. Next slide. We can see the little one blowing the big one up. But a lady in Slovakia took this to her students, and they investigated the pressure in a balloon, because it's the pressure that pushes the air, not the size, isn't it? Size isn't quite the most important thing, it's what's inside. So if we go to the next slide, you can see that graph of pressure in a balloon versus the size of the balloon, right? The size along the bottom, the balloon radius, so that at first the pressure is very big. Can you see that just above the is it? I can't quite see on my computer. 2, I think, where the other. It starts very high, and then it starts high, and then it comes down and up again. So at where the balloon is generally being blown up in the bottom part, the pressure is less, whereas the pressure is much higher at the beginning. So you can do a qualitative assessment of that. Of course, it goes high at the end again just before it bursts, so you can get the reverse effect if you're really clever. Click on, that's shown in the next slide, but we'll move on quickly. You Yeah, it's quite interesting that you can't blow two balloons up at the same time without one being blown first. But then something else, there may be a question of something that you don't really know the answer at all. Either you know or you don't. An example I have of that are these little tops. I don't know if you have these in Argentina. One of my hobbies is spinning tops. Click on. So if you spin a top, there's one. Spin a top with a big round bottom like that. What happens? What happens as you spin it? Does it? I think there's like no, some tops sort of will wobble a bit and then erect themselves so they get going. A whipping top does that. Do you know what happens to this sort of top? It's called a tippy top. I don't know that I can do it in front of you here, but if you spin it, it's down there. He did that. It's just got to spin fairly fast. See, it tries to stand up on its end. Try this one. Just not spinning it fast enough. There we go. See how it stands up on its end? It turns upside down. Now, if you didn't know that, you wouldn't get that right. But it's an interesting. If you go back to the slides, and go to the next one, and you can see the top at the bottom. It moves. It goes over slightly to the side, and then the tip hits the surface, and then it stands up on its end. It's a very good example of something to observe, that, because if you think about it, in order to turn upside down and conserve its angular momentum, the top has to stop halfway through. Right, next slide. So that if you start with something that's too hard, then people are. Next slide. So we're going to have a quiz. Now, what I'm going to do, I'd like you to, if you've got the answer paper, I don't know if you've got that, but just make a note of your answers as we do this. And try and put yourselves in the position of the children, because some of these things you don't know. And if you're sitting in a class and you don't know, you sort of hibernate. You try and hide from everyone. So I'm going to go through as many as I can get through in the time, little questions, and we'll see how many you get right. But nobody's going to know but yourself. So there we go. So the first one, always start with a nice easy thing. Next slide is a cylinder. You can just keep on me. I've got a cylinder, which is just a cup. I've got a bit of rope in it, for a cup like that. And I ask the question, which is the largest, the high circumference? Which do you think is largest? Now you can imagine a group of children would get involved, I hope, with discussing it. It's not a threatening question, it's just how you see that, which is largely. What would you say? So you write your answer down. And look carefully. Surely, that's just sort of a few centimeters. Oh, that's quite. But let me show you a surprise. So I can get my fingers around there like that. Just about reach, not quite. But if I stretch them out and they're not straight, they go way beyond the top of the cup. If I have my rope, I can show this. That's the rope round. There we go with the rope. Hold on to the bottom and hold it up to the top. And you can see that the rope going around is much longer. I found this tube in a toy shop. Now this is lovely to say to your children once they've done it and they've worked out that the height is much less than the circumference all the way around. How could that be? And then I have 1, 2, 3 balls. And I did this with quite a young class in the Netherlands. And one girl straight away put her hand up and said, well, 3 diameters, 6 radii, and the circumference is 2 pi r, or pi times d. And pi is 3.1416159, etc., etc. And that's only 3D. So 3D, pi d. So I like that because it sort of you can do it in different ways. So that's number 1. I hope you got that right, that the height is less than the circumference of those beaks. But you could try different shapes and so on to do that. It's very hard to judge curved distances with straight distances. Next, number 2 is is it an orange next? Click, there's the slide. An orange, another nice easy one to start with. So if we have an orange and we float the orange in water, I've got pictures of all this, so I don't need to do everything, but we float the orange in water, it floats, right? If I peel the orange, if I take the skin off the orange, will it float or will it sink? I'll go to the next slide, if I got myself right. Oh no, go back from that slide. You've seen the answer. So will it float or will it sink when you take the peel off? And so you've seen the answer, so you've got an answer. So I cheated a bit. So when you take the peel off, the orange actually sinks. So why does it sink? Because the orange is lighter when you've got the skin off. But go on to the next slide. The skin acts as like a buoyancy aid that you have in the swimming baths. So it's about average density and so on, sinking and floating with density. But that's a nice, so most people get that right straight away. There's quite a lot I like to do with fruit. Floating and sinking fruit, different fruits, some float and some sink. Next one, well, we've got an orange. There we go. There's another one that it's amazing how many people get this wrong. So we have an orange and a beaker of water on the scales, and it reads 235 grams. Now, suppose we take the orange and put it into the beaker of water. What will happen to the reading on the scales? Will the balance stay the same? Will it be unchanged? I hope you're thinking about these things and not just sitting back drinking a beer. Because you can do that when you're online. You can't do it in the classroom. Will the balance be unchanged? Young children will get this wrong because in their heads, they think things weigh less in water. But older children will probably get it right because the reading stays exactly the same. You've still got a beaker of water, you've still got the orange, and you've still got the balance. So you can move on to the next slide and see that it stays the same. It's still 235. With the older children, of course, you can then discuss the forces. How is it that the orange weighs less in water? And you've got upthrust. So if you have an upthrust, you have a downthrust, and so on. you're into Newton's third law and so on. Let's go on to the next one, because the children get that one wrong. The next question with the balance is with your finger. What happens to the reading when you put it without touching the sides? Will the reading stay the same, or will it go up? Or will it go down? It's an area people can get very confused by trying to work out the forces. For younger children, I would say that the reading goes up is the answer. Younger children, if you look at the beaker, when you put your finger in, the water level goes up. So the balance believes, if that's the right way to put it, it's not very scientific, but the balance thinks there's more water in the beaker. So there's a bigger depth of water, so there'll be a bigger pressure at the bottom, so there'll be a bigger force. You could also argue that if you put your finger in, there is an upthrust from the water, and therefore there's a downward force from the finger to make the reading increase. All right, next, another one. That's just that one going through. Another one, and I like this. This, I wish when I taught, I'd known this. I've got a frying pan, the very frying pan that's in the picture. Right, can you see that? My wife doesn't like me showing this, but it was an old one that I had away camping, and it's not one that we've used. And I've got some ice somewhere. Children are quite fascinated that you can keep ice in a thermos flask. You know, they normally think that keeps things hot, but why does it keep things cold? Because heat can't get in. That is true. So I'm going to put an ice block on my frying pan, and if I can find it, also on this you see them on the table. Get rid of the bowl I had. You see them on the table. Well done. And what will happen? Now you can confuse the children by saying, feel that, that feels quite warm. That feels cold. Why does it feel cold? We know that one. I get the ice. I need two bits that are more or less the same size. Put number one on the box and number two on the pan. Which one will melt first? Will they both melt the same? You can go on to the next slide, Julian. It's a bit complicated, the questions as to which one is going which one A, B, C, D. But which one will melt first? And this happens as we're talking. That's the beauty. I used to do conduction of material using lagging, and we used to spend a whole lesson waiting for something, high heat to pass through a little calorimeter. But I think you can see that ice is just melting straight away. You see that? I think you kind of don't want to get water on the computer. But that's all messy and melted. Whereas there's absolutely no sign of melting with this one. Why? Because the plastic is a poor conductor, so heat can't get through to the ice, whereas the pan is a good conductor, being a thick metal block. I quite like to, there's other things, you can do this with other bits and pieces, a piece of metal. If you want to defrost something, some meat, quickly, you put it on a metal sheet and it will defrost because the heat can move to it, which the children have quite enjoyed. And then you can to discuss. Go next slide, please. With 2 cans, one of Pepsi and one of Cola. Now they may have they changed these things, but the Pepsi and the Coca-Cola can is aluminium, and aluminium is a much better conductor of heat than steel. So you can put these are empty cans, and I've placed them in little sources of hot water just to speed things up. And the ice on the cola can, the aluminium, melts much quicker than the ice on the steel, which is a poorer conductor. So that's the sort of extension of that. Next. And there you see it, just about. Next slide. Forces. I'm racing through all sorts of things. I like doing this. I don't know whether we can get it on the screen, but I've got a slinky spring here. You know these things? You should use them for waves. And if I hold this up, stretch it out, and I leave go, the question is, what will happen to this little man here? He's doing a dive bomb at the moment. What will happen to him the instant that I leave go? Will he go up before he goes down? Everything's going to fall to the floor eventually. Will he go up? Will he stay where he is for a moment, like the cartoon character, you know, that goes, wait, oops, down he goes? Or will he just go down straight away? This is a question about forces and about balanced forces. So what will happen? What do you think, ABC? Well, at great risk, I'm going to just climb up here. I'll try and get it in the picture. Can you still see the little man? Just hopefully watch the little guy very carefully. 3, 2, 1. He's going to stay still for a moment. 1, 2, 3. Well, I couldn't see my screen there, but did you? Because at the instant that you drop this, the forces are balanced. The spring is pushing up, the earth is pulling down. The spring is pulling up. And they're balanced until the spring contracts. Then, once he's fallen, it's a free fall situation. So the man, in falling, things become weightless and the spring contracts. And so it falls, eventually hits the ground like that once you've left go. Can work out that as forces. Next slide. And I did this in a big house. And there you see the beginning and then the end where it's falling all together. Now that brings us to free fall. Where are we? Free fall. Can you go on to the next slide? I can't do this because I'm in my house. I've ever done this with a bottle of water that's spouting like that, and I'm going to throw it up in the air, and I want to know what's happened to the jet of water. Does the jet stop? Does it only stop at the top? Does it come out more at the bottom? You can discuss this for a long time. Go to the next slide. I think I've got myself in the garden. Or does it stop once as soon as the bottle's left the thrower? Is it stronger on the way up and less on the way down? Does it stop at the top when the bottle stops, or something else? I did this with a group of 18-year-olds and 17-year-olds. And the physics teacher was at the back of the class. And the boys, it was mostly boys, they came out with the most outrageous statements. And the physics teacher was pulling his hair out because he just taught all this. But what happens is that if we go to the next slide, I think you can see that the jet comes out, but when it's in the air, there's no jet at all. And that's because it's in a state of free fall. And the water relative to the bottle is weightless, so there's no jet coming out. And move on. There's all sorts of things where you can do experiments where you can, on the next slide, throw things up in the air. I usually do this with a tube of water as well, which if you throw it up, the water doesn't come out as long as you keep your finger on the end to the last minute, throw it up. Or easier is to use one of these things, right? Now what will happen when I throw that in the air? The weight inside the box becomes weightless relative to the box, so it doesn't sound. See that? It's not sounding while it's in the air. Oh, you can get these, call these groan tubes. You can throw them. Or when you drop it. Don't need to throw it up, you can just drop it in free fall. Drop it in free fall, so weightless. That you can introduce all sorts of things to do with space with that, or recap. Next slide, it's up to number 7. How's the time? 10 to. So there's my grandson a few years ago with the groan tube. Next slide. Next slide. Here's another nice weightless one. I've got 2 very heavy weights there, and the toilet roll is held between the 2 weights. And I want to know what will happen to the toilet roll when I drop the weights. Will the toilet roll be pulled out? Sorry, I'm still playing with this. Will the toilet roll be pulled out? Will it just leave go, or what? Will something happen? The toilet roll does not unwind. Let's see. The toilet roll unwinds. Or the toilet roll unwinds a little bit, or what? Now, go on to the next slide. And you can do this with, I realized I didn't, the weights are great because they make a really heavy clang. But you can do it with, if you get the two really heavy books like this. So I've got the 2 heavy, book of the universe and a Bible dictionary, which are the biggest books I've got. If I drop this, should work this, ready? Will the paper come out? The answer is it doesn't, because the top book becomes weightless relative to the bottom book in free fall. So the only reason that the top book is pushing on the paper is that the bottom book is pushing up on the top book. So if I leave go, ready? Oof, landed on my toe. Never mind. Now you know, there's an interesting teaching point there. If you'd done that in the class and it had landed on your toe and broken your toe especially, the children would never forget. They'd never forget that day of the experiment with the toilet roll. But anyway, you saw that the toilet roll wasn't pulled out, so the top book was weightless. But there you go. That's a good little teaching point. There have been 1 or 2 disasters in my teaching career where experiments haven't worked, and those are the ones that the children remember. Next, I'll do a couple more and then we'll we'll skip on. There's the toilet roll not come out. And another of my grandchildren with Newcastle United strip on. Next. We skipped this, I think. 2 balls. Children get just dropping the 2 balls. Which one reaches the ground first? Table tennis ball or the golf ball. And they will often say that the golf ball will get there first, but over a short distance, the air resistance isn't significant, so they both land together. So if you listen, you'll only hear one click. The second click was the second bounce. Okay, move on. We're gonna rattle through these quickly, so there's time at the end. Now, next one, we've done that. Next, you can drop all sorts of things. Quite a tip is to do a stick and then divide it into 5 and have the little bits and drop them together. 2 tennis balls, I have one filled with water, so it's really heavy, and one that isn't filled with water, you can just inject it, and they both drop together. Unless, with these things, you go up 3 stories, so the air resistance suddenly becomes significant. Next. This is one of my favourite ones. This is why I'll stop after this. You see that ice on there is still not melted, whereas it's disappeared altogether on the front side on the floor. Now, I'll really make you answer this one if I can find. You can see this. This is just a piece of flexible board, and I've wedged it up at the sides with some wood. And I've got a can of Coke, and younger children love this because they can count, and we get them counting in different languages and different countries. So if you just count how many times it goes backwards and forwards as I'm talking, should do about 40. 1, 2, 3, 5, 8, 9, 10, 11, 12, 13, 16, 17, 18, 19, 20, 23, 24, 25, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 48, 49, 50. It's just about stopped 50 times. Now, the question I ask is, give it a good shake, do it again. What will happen? Will there be fewer or less? Fewer backwards and forwards or more? You get all sorts of answers and all sorts of reasons. Because if you do it again, it actually 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 23, 24, exactly half. Now, why would that be? You'll get children who say, well, it's heavier because it's got bubbles in now. That's an interesting thought that they might have. I thought it was the pressure, but it isn't the pressure. The pressure is the same inside. It is actually the bubbles. If you move to the next slide, go to the next slide, you can see the bubbles, and the bubbles are dragging. There's a dragging force of the bubbles. And when you can get rid of the bubbles, do you know how to get rid of the bubbles? You must do this with a can of beer to stop it fizzing. That gets rid of the bubbles, and it will go back to doing 40. But lots of interesting things you can do with that. It's a nice one. Now, I think what we'll do is just race through the last few slides, and I'll just talk quickly over them. A big circuit, an electricity circuit that goes all the way around the classroom. use diodes which don't have a heating issue, and you have a bulb near the battery and a bulb far away, you'll always get people who say the one far away will take longest before it comes on, but they both come on together because of the way that electric currents work. No, the next one, that's one a bit about electricity. One about this is a nice one to do with an inertia to knock the placemat away from the things above it, and the juggling bags fall directly down into the beakers. It's slippy on the bottom, it's not so slippy, and it knocks these sweetie tubes out the way, and the only force on the bags on the top is downwards, so they have to fall down. You can get the weakest child to do that and be successful. Let's see what happened with me. Next slide. Yes, and they all went in. Give it a good whack. If you get somebody worrying about it, it doesn't work. But if you give it a good whack, they go next. Oh, and that's the alternatives if I was doing this as a quiz. I've not really done it as a quiz for you. I've just rattled through. So that's the alternatives. Next. Blowing up. This is a nice one. I don't know if you... These polystyrene beads in a balloon from a scatter cushion. These little beads, and if you blow the balloon up, it's a clear balloon, you get this lovely effect. Can you see that with the beads all spread out? If, on the other hand, you blow the balloon up with your breath, the breath is wet, so the electrostatics doesn't work. That's I don't know if you have that problem. Probably think it rains all the time in England, so we never do electrostatics experiments in the rain. So when you blow it up like this, oops! Oh dear me, that was clever. Now everybody would remember that. Did you see the balloon burst? And the balls are all over me. But go on to the slides. Go on to this next slide. There's make it big. Make the slide big, make me small. And then the next, there's them spread out. The next slide, you can see one that I've used where I've blown. That was really cute, and the thing burst. There's polystyrene balls all over this room. I'll get my card. Next, go on to the next one. I think that might be nearly the last. Oh, this was a yen, aluminium yen, or you can use a can and try and move it with electrostatics, which is an unusual outcome because, in fact, the water is more attractive than the aluminium yen. Move on. Move on, move on, move on. Just keep moving. And then these words in the mirror. If you go to the next slide, you can see that icebox looks the same, but fridge is inverted, and that's because of the symmetry of the letters. You can make all sorts of different things up with your own language for that. We can look at that later. Next, and I think there's a selection of English words, but you want Spanish words. Next, and move on, just flick through that. Flick through that. Next, 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 next. So all these experiments are being published if you go to me now, in physics education, but although you'd have to pay to get a hold of a physics education, I've arranged for them all to be free to download. All these articles at the end. There's one that we haven't done about 4 candles, and you get the question in much more scientific details, and then the answer. The answer's in the next edition. But that reference there, if you just Google what happens next, physics education, what happens next, you get to the next slide, you get to a page which lists all the years since I've been doing this, and every edition has one in. And then you click on one of those years, and it shows you, click on, next, next, and it gives you the details of what the experiments are, and then you can click on there and you get the actual articles, and that's all free. You don't have to pay for any of that. But you do if you wanted to have all the articles in physics education, but mine are all right. But they've also published some of the experiments on just a sheet. If I was with you, I would give you all one of these, but I can't. And then the other way you can get to these experiments, click on, next, is since lockdown began, I started a Facebook group called What Happens Next Experiments. It's a private group, but I don't stop anybody joining. I just want to make sure you're not a robot. So I ask you, like, where you're from, do you teach or something like that. If you answer the questions, I let you in. And now there's 100 of these experiments. So you can liven up your lessons with 100 different experiments. That's sort of 2 years worth of weeks. Every week you could do a different one. And some are great and some aren't so good. And some are done by different people. In fact, it would be nice to have one done by somebody in Argentina that we can publish in the next month or so. So there's 100 experiments there that you can, again, freely look at. And I've got them all those experiments on my computer. So if you want, it's a single one, I can send it to anybody. Next. So that's the end of my little chat. I hope that's given you an idea of some ways in which you can engage children, just getting them talking and so on. When I was at school, physics practicals and a lot of physics was very much out of the textbook and quite boring. Really, I don't know how on earth I became a physics teacher. We did experiments where we had to prove the angle of incidence equals the angle of reflection. We knew the answer before we started, and we sort of fiddled our books so that we got the right answer. Whereas now we sort of want to explore things and discuss right from the word go in primary school, right up. And those inquiring minds need sort of feeding with these little ideas and so on. So I hope that's given you some idea of some of these things. I hope you tap into either the physics education articles or even the Facebook group. And there'll be a new experiment tomorrow. So that's something you might even look forward to. But there's 100 previously. So there we are, Julian. I've done my bit. Do you want to come back, and anybody want to ask anything or about my life, my anything, my football team, whatever. Well done, Argentina last weekend, beating the All Blacks. That really, that actually pleased me.
Thank you, David, for your great presentation. And well, now questions are allowed. Habilitamos la sesión de preguntas para todos y todas. Let's wait a little bit. There were some comments. What did you say, David? Sorry?
I could show an experiment again if they missed something. You know, I've got the stuff all over, apart from the balloon that burst.
Okay. Él dice que puede volver a hacer algún experimento si quieren. Cecilia says,
if you put it that way, it wouldn't work because the air has to go up. You know, it's all right doing it that way, but if you do it that way, the air's got to go up. But in fact, still works going up.
Cecilia says, I would love my students to remember, but I prefer no injuries. Haha. And Francisco Castañaga says he has an excellent point about accidents in class. So let's wait for comments and questions. Janina Torres says, thank you for sharing, really interesting and amusing.
Especially when the book fell on my foot.
Cecilia says, I really love that you didn't talk about things, you show them. Do you have some recommendations for large courses?
For large courses?
Yeah.
How does she mean large?
I think that people with classrooms with many people.
Yes, well, that's where at the beginning, depending on how many people you've got, if you want to do it and get everybody involved, I would much prefer different tables where you have 4 or 5 people or 3 or 4 people at each table. It's much easier to get people competing with each other. So if I've done it, was a few years ago in Norway, and we had, I don't know, about 70 children, and we had them all at different tables in a big hall, and I had a big screen with and I had the demonstrations on as well, and I did the demonstration. Some of them, they had apparatus to try at their tables, but we did it as a competition. And the children really, got quite involved with that. So that's one way to do it with a lot of people. But you can do it with an audience, but you tend, as I've done there, to skip on from one. You can't you can get people to mark. I did do it with little gizmos where everybody had a computer. I'm not sure what you call them. So they had to enter A, B, C, D. And then we got on the screen how many A's, how many B's, how many C's. And that enabled you to say, right, so this 60% have said this, but 30% have said this wrong answer. So you could explore the wrong answer. Often you learn more by mistakes than you do by getting things right every time. So with the modern technology and using these ABCD, you have a record of your class. If you did a few, you can do a few on free fall or a few on density or a few on light. At the end of a session, you've got a record that nobody understood something. That there was one area that it can teach you how the bit that you need to reinforce, as it were, or the particular thing that everybody gets wrong. That's the sort of modern slick way to do it. I've done it that way, where they've had the technology.
Él dice que divide a los cursos entre 4 y 5 personas. En Noruega hizo eso, también hizo una competición, ha utilizado dispositivos para poder ver qué es lo que responden, qué es lo que responde el alumnado, también usando una pantalla. También comentó que a veces, que así, digamos, se tiene un feedback de qué respuestas correctas e incorrectas, y él también comenta que de las respuestas incorrectas se aprende más. Bien, let's move on to the next question. Nicolás is asking, do you think TV shows have any influence on science perception?
I'm sure they do. It's interesting that university applications for subjects can be greatly influenced by what is the popular television show of the day. There were some programs about sort of engineers building bridges and things, and then there seemed to be a lot of people wanting to do that because this guy in Dundee was very interesting, that people choose their subjects for all sorts of illogical reasons, that they like a television show or that their uncle went to Australia and did something. So there's that side. The other thing is that it annoys me a little bit about a TV show is that they will be very slick. It is very slick. Do you know what I mean? It's sort of everything runs very smoothly. And you realize that the science show has the person at the front doing the experiment. There's 6 people running around after him getting everything right. It's probably recorded and recorded again. And they will probably in 30 minutes do the experiments that you want to do in 6 weeks. In school, you know, they cram lots of, and they do all the exciting things. When I first retired, I did some lectures on light. It was color, and somebody did color in chemistry, and I did color in physics, and somebody else did color in psychology. And the 2 people that did the other 2, the chemist was a professor from the university. I'm just an ordinary teacher. So I was on my own doing all these color demonstrations. And the guy from the university had 3 technicians. So it was him at the front, but there were 3 people running around afterwards. You look at a television program and there's about 20 people.
Yeah.
So if you look at my What Happens Next experiments on Facebook, they're nearly all recorded in one show. So there's mistakes that happen, and I've left them in because I think that's reality. So the TV will interest children. I think a lot of the global warming things, there's been television programs on pollution and so on. There have been a lot of programs which have really influenced children to be interested in those things, which, 30, 40 years ago, there just weren't that type of program. So I'm sure TV has a great influence on children these days. Perhaps more, how much more is it the internet now that people are getting ideas from? I think, there's a lot of good things about the internet and some bad things as well. So does that answer your question? I've just rambled on.
Let's see what he comments. I'll translate. Él lo que dice es que sí, influencia, que tiene influencia la televisión, que niñes ven más info del calentamiento global, de contaminación. Él también lo que comenta es que en su material él muestra los errores y que en televisión se muestra que todo es ideal y que no existen los errores, todo funciona perfecto. Y que hay programas que tienen como 20 personas que están encargándose que todo funcione bien. Okay, let's see. Ilan asks, who orders the plays for you after class?
Who tidies up?
Yeah.
Well, I think I better tidy up here. When I do my lectures, if my wife is with me, she is excellent at packing everything away into my cases, you know, when I've got a lot of apparatus. And I'm afraid I tend to push everything in. I'm not so tidy. But no, I'll be tidying up, I think, tonight. Well, I might leave it till tomorrow because it's nearly 9:30 in England.
Okay. So do you think, David, that we should end now?
Yeah, that's fine. I'll show you one more thing before I go. But
okay.
Feel free, if people want the PowerPoint to go through, feel free to let them have it. And on that, there's, you know, my address and everything. Let me finish with one thing to show you. Okay. I want to know, how does this work? So here we have, if I show you, a hexagon and a square, right? You can see that. Now just cover it up, and it is now 2 circles. So tell me how that works. Hexagon and a square. And I'm not turning it upside down. I'll show you exactly what I do. I'm turning it around. Isn't that clever? So, well, good evening and good night.
Good night, David. Thank you very much.
Goodbye from England.
Bye bye. Yo, por último, les quería comentar. En mi caso, esta es la última charla que voy a estar coordinando. Les agradezco a todos y todas por haber participado del ciclo de charlas. Agradezco especialmente al Departamento de Física. Este ciclo de charlas no podría haberse hecho sin su apoyo logístico. También agradezco a todas las personas a las que le escribí para preguntarles por consejo para la organización de las charlas y a las que ayudaron con la difusión, y a todas las personas que me escribieron para felicitarnos por el ciclo de charlas. Quiero recordar que los certificados van a estar luego de finalizado el ciclo de charlas, y que la próxima charla va a ser el viernes a las 7:30 de la tarde. Y en cuanto a la organización, voy a buscar si hay preguntas. Preguntaron por el día y el horario, eso ya está. Es la última charla. A ver si quedó alguna pregunta más. Después vamos a subir la información, la vamos a subir en la descripción del video de las cosas que pasó David. Marina Ganser, los links. Yo voy a agregar en la descripción y en los comentarios, hay un link que se va actualizando con las charlas nuevas, y yo creo que entre lunes y martes va a estar. A veces no está lunes a la mañana, pero entre lunes y martes. Yo ahora lo adjunto. Así que bueno, muchas gracias a todos y todas, y nos vemos la próxima. Hasta luego. Chao, chao.